Geometry is a branch of mathematics concerned with questions of shape, size, relative position of figures, and the properties of space. A mathematician who works in the field of geometry is called a geometer. Geometry arose independently in a number of early cultures as a body of practical knowledge concerning lengths, areas, and volumes, with elements of formal mathematical science emerging in the West as early as the ALS. By the 3rd century BC, geometry was put into an axiomatic form by Euclid, whose treatment, Euclidean geometry, set a standard for many centuries to follow. Archimedes developed ingenious techniques for calculating areas and volumes, in many ways anticipating modern integral calculus. The field of astronomy, especially as it relates to mapping the positions of stars and planets on the celestial sphere and describing the relationship between movements of celestial bodies, served as an important source of geometric problems during the next 1.5 millennia. In the classical world, both geometry and astronomy were considered to be part of the quadrivium, a subset of the 7 liberal arts considered essential for a free citizen to master. The introduction of coordinates by René Descartes and the concurrent developments of algebra marked a new stage for geometry, since geometric figures such as plane curves could now be represented analytically in the form of functions and equations. This played a key role in the emergence of infinitesimal calculus in the 17th century. Furthermore, the theory of perspective showed that there is more to geometry than just the metric properties of figures. Perspective is the origin of projective geometry. The subject of geometry was further enriched by the study of the intrinsic structure of geometric objects that originated with Euler and Gauss and led to the creation of topology and differential geometry. In Euclid's time, there was no clear distinction between physical and geometrical space. Since the 19th century discovery of non-Euclidean geometry, the concept of space has undergone a radical transformation and raised the question of which geometrical space best fits physical space. With the rise of formal mathematics in the 20th century, space lost its intuitive contents. So today one has to distinguish between physical space, geometrical spaces and abstract spaces. Contemporary geometry considers manifolds, spaces that are considerably more abstract than the familiar Euclidean space, which they only approximately resemble at small scales. These spaces may be endowed with additional structure which allow one to speak about length. Modern geometry has many ties to physics, as is exemplified by the links between pseudo-Riemannian geometry and general relativity. One of the youngest physical theories, string theory, is also very geometric in flavor. While the visual nature of geometry makes it initially more accessible than other mathematical areas such as algebra or number theory, geometric language is also used in contexts far removed from its traditional Euclidean provenance. Overview. Because the recorded development of geometry spans more than 2 millennia, perceptions of what constitutes geometry have evolved throughout the ages. Practical geometry. Geometry originated as a practical science concerned with surveys, measurements, areas, and volumes. Among other highlights, notable accomplishments include formulas for lengths, areas and volumes, such as the Pythagorean theorem, circumference and area of a circle, area of a triangle, volume of a cylinder, sphere, and a pyramid. A method of computing certain inaccessible distances or heights based on similarity of geometric figures is attributed to Thales. The development of astronomy led to the emergence of trigonometry and spherical trigonometry, together with the attendant computational techniques. Axiomatic geometry. Euclid took a more abstract approach in his Elements, one of the most influential books ever written. Euclid introduced certain axioms, or postulates, expressing primary or self-evident properties of points, lines, and planes. He proceeded to rigorously deduce other properties by mathematical reasoning. The characteristic feature of Euclid's approach to geometry was its rigor, and it has come to be known as axiomatic or synthetic geometry. At the start of the 19th century, the discovery of non-Euclidean geometries by Nikolai Ivanovich Lobachevsky, Janos Bollier and Carl Friedrich Gauss and others led to a revival of interest in this discipline, and in the 20th century, David Hilbert employed axiomatic reasoning in an attempt to provide a modern foundation of geometry. Geometric constructions. Classical geometers paid special attention to constructing geometric objects that had been described in some other way. Classically, the only instruments allowed in geometric constructions are the compass and straight edge. Also, every construction had to be complete in a finite number of steps. However, some problems turned out to be difficult or impossible to solve by these means alone, and ingenious constructions using parabolas and other curves, as well as mechanical devices, were found. Numbers in geometry. In ancient Greece, the Pythagoreans considered the role of numbers in geometry. However, the discovery of incommensurable lengths, which contradicted their philosophical views, made them abandon abstract numbers in favor of concrete geometric quantities, such as length and area of figures. Numbers were reintroduced into geometry in the form of coordinates by Descartes, who realized that the study of geometric shapes can be facilitated by their algebraic representation, and for whom the Cartesian plane is named. Analytic geometry applies methods of algebra to geometric questions, typically by relating geometric curves to algebraic equations. These ideas played a key role in the development of calculus in the 17th century and led to the discovery of many new properties of plane curves. Modern algebraic geometry considers similar questions on a vastly more abstract level. Geometry of position. Even in ancient times, geometers considered questions of relative position or spatial relationship of geometric figures and shapes. Some examples are given by inscribed and circumscribed circles of polygons, lines intersecting and tangent to conic sections. The Pappus and Menelaus configurations of points and lines. In the Middle Ages, new and more complicated questions of this type were considered. What is the maximum number of spheres simultaneously touching a given sphere of the same radius? What is the densest packing of spheres of equal size in space? Most of these questions involved rigid geometrical shapes, such as lines or spheres. Projective, convex, and discrete geometry are three subdisciplines within present-day geometry that deal with these types of questions. Leonhard Euler, in studying problems like the Seven Bridges of Königsberg, considered the most fundamental properties of geometric figures based solely on shape, independent of their metric properties. Euler called this new branch of geometry geometricitas, but it is now known as topology. Topology grew out of geometry, but turned into a large independent discipline. It does not differentiate between objects that can be continuously deformed into each other. The objects may nevertheless retain some geometry, as in the case of hyperbolic knots. Geometry beyond Euclid. In the nearly 2,000 years since Euclid, while the range of geometrical questions asked and answered inevitably expanded, the basic understanding of space remained essentially the same. Immanuel Kant argued that there is only one, absolute, geometry, which is known to be true a priori by an inner faculty of mind. Euclidean geometry was synthetic a priori. This dominant view was overturned by the revolutionary discovery of non-Euclidean geometry in the works of Bollier, Lobachevsky, and Gauss. They demonstrated that ordinary Euclidean space is only one possibility for development of geometry. A broad vision of the subject of geometry was then expressed by Riemann in his 1867 inauguration lecture über die Hypothesen, welche der Geometrie zugrunde liegen, published only after his death. Riemann's new idea of space proved crucial in Einstein's general relativity theory, and Riemannian geometry, that considers very general spaces in which the notion of length is defined, is a mainstay of modern geometry. Dimension. Where the traditional geometry allowed dimensions 1, 2 and 3, mathematicians have used higher dimensions for nearly 2 centuries. Dimension has gone through stages of being any natural number n, possibly infinite with the introduction of Hilbert space, and any positive real number in fractal geometry. Dimension theory is a technical area, initially within general topology, that discusses definitions, in common with most mathematical ideas. Dimension is now defined rather than an intuition. Connected topological manifolds have a well-defined dimension. This is a theorem rather than anything a priori. The issue of dimension still matters to geometry, in the absence of complete answers to classic questions. Dimensions 3 of space and 4 of space-time are special cases in geometric topology. Dimension 10 or 11 is a key number in string theory. Research may bring a satisfactory geometric reason for the significance of 10 and 11 dimensions. Symmetry. The theme of symmetry in geometry is nearly as old as the science of geometry itself. Symmetric shapes such as the circle, regular polygons and platonic solids held deep significance for many ancient philosophers and were investigated in detail before the time of Euclid. Symmetric patterns occur in nature and were artistically rendered in a multitude of forms, including the graphics of M.C. Escher. Nonetheless, it was not until the second half of 19th century that the unifying role of symmetry in foundations of geometry was recognized. Felix Klein's Erlangen program proclaimed that, in a very precise sense, symmetry, expressed via the notion of a transformation group, determines what geometry is. Symmetry in classical Euclidean geometry is represented by congruences and rigid motions, whereas in projective geometry an analogous role is played by collineations, geometric transformations that take straight lines into straight lines. However, it was in the new geometries of Beaulier and Lobachevsky, Riemann, Clifford and Klein, and Sophus Lie that Klein's idea to define a geometry via its symmetry group proved most influential. Both discrete and continuous symmetries play prominent roles in geometry, the former in topology and geometric group theory, the latter in Lie theory and Riemannian geometry. A different type of symmetry is the principle of duality in projective geometry, among other fields. This meta-phenomenon can roughly be described as follows. In any theorem, exchange point with plane, join with meet, lies in with contains, and you will get an equally true theorem. A similar and closely related form of duality exists between a vector space and its dual space. History. The earliest recorded beginnings of geometry can be traced to ancient Mesopotamia and Egypt in the 2nd millennium BC. Early geometry was a collection of empirically discovered principles concerning lengths, angles, areas, and volumes, which were developed to meet some practical need in surveying, construction, astronomy, and various crafts. The earliest known texts on geometry are the Egyptian Rhind Papyrus and Moscow Papyrus, the Babylonian clay tablets such as Plimpton 322. For example, the Moscow Papyrus gives a formula for calculating the volume of a truncated pyramid, or frustum. South of Egypt, the ancient Nubians established a system of geometry including early versions of sun clocks. In the 7th century BC, the Greek mathematician Thales of Miletus used geometry to solve problems such as calculating the height of pyramids and the distance of ships from the shore. He is credited with the first use of deductive reasoning applied to geometry, by deriving 4 corollaries to Thales' theorem. Pythagoras established the Pythagorean school, which is credited with the first proof of the Pythagorean theorem. Though the statement of the theorem has a long history, Eudoxus developed the method of exhaustion, which allowed the calculation of areas and volumes of curvilinear figures. Around 300 BC, geometry was revolutionized by Euclid, whose Elements, widely considered the most successful and influential textbook of all time, introduced mathematical rigor through the axiomatic method and is the earliest example of the format still used in mathematics today. that of definition, axiom, theorem, and proof. Although most of the contents of the elements were already known, Euclid arranged them into a single, coherent logical framework. The elements was known to all educated people in the West until the middle of the 20th century, and its contents are still taught in geometry classes. Today, Archimedes of Syracuse used the method of exhaustion to calculate the area under the arc of a parabola with the summation of an infinite series, and gave remarkably accurate approximations of pi. He also studied the spiral bearing his name and obtained formulas for the volumes of surfaces of revolution. Indian mathematicians also made many important contributions in geometry. The Satapatha Brahmana contains rules for ritual geometric constructions that are similar to the Sulba Sutras. According to the Ulba Sutras contain the earliest extant verbal expression of the Pythagorean theorem in the world, although it had already been known to the old Babylonians. They contain lists of Pythagorean triples, which are particular cases of Diophantine equations. In the Bakshali manuscript, there is a handful of geometric problems. The Bakshali manuscript also employs a decimal place value system with a dot for 0. Aryabhata's Aryabhatiya includes the computation of areas and volumes. Brahmagupta wrote his astronomical work Brahma Sphuta Siddhanta in 628. Chapter 12, containing 66 Sanskrit verses, was divided into two sections: basic operations and practical mathematics. In the latter section, he stated his famous theorem on the diagonals of a cyclic quadrilateral. Chapter 12 also included a formula for the area of a cyclic quadrilateral, as well as a complete description of rational triangles. In the Middle Ages, mathematics in medieval Islam contributed to the development of geometry, especially algebraic geometry and geometric algebra. Al-Mahani conceived the idea of reducing geometrical problems such as duplicating the cube to problems in algebra. Thabit ibn Qurra dealt with arithmetic operations applied to ratios of geometrical quantities, and contributed to the development of analytic geometry. Omar Khayyam found geometric solutions to cubic equations. The theorems of Ibn el-Haytham, Omar Khayyam and Nasir al-Din al-Tusi on quadrilaterals, including the Lambert quadrilateral and Sakkari quadrilateral, were early results in hyperbolic geometry, and along with their alternative postulates, such as Playfair's axiom, these works had a considerable influence on the development of non-Euclidean geometry among later European geometers, including Witello, Gersonides, Alfonso, John Wallis, and Giovanni Girolamo Saccari. In the early 17th century, there were two important developments in geometry. The first was the creation of analytic geometry, or geometry with coordinates and equations, by René Descartes and Pierre de Fermat. This was a necessary precursor to the development of calculus and a precise quantitative science of physics. The second geometric development of this period was the systematic study of projective geometry by Gerard Desargues. Projective geometry is a geometry without measurement or parallel lines, just the study of how points are related to each other. Two developments in geometry in the 19th century changed the way it had been studied previously. These were the discovery of non-Euclidean geometries by Nikolai Ivanovich Lobachevsky, Janos Bollier and Carl Friedrich Gauss, and of the formulation of symmetry as the central consideration in the Erlangen program of Felix Klein. Two of the master geometers of the time were Bernhard Riemann, working primarily with tools from mathematical analysis, and introducing the Riemann surface, and Henri Poincaré, the founder of algebraic topology and the geometric theory of dynamical systems. As a consequence of these major changes in the conception of geometry, the concept of space became something rich and varied, and the natural background for theories as different as complex analysis and classical mechanics.